Hello and welcome to this presentation. We are going to be discussing about the topic of music genre classification with deep learning methods. But first, I think it's better to introduce myself a little bit. My name is Lempesi and I am final year ECE undergraduate at National Technical University of Athens. I started working at Orfium at the beginning of September as part of my internship, and now I will continue my journey there as a junior data scientist. My project during my internship, which now became my thesis topic as well, was music genre classification with deep learning. This is why we are going to be discussing about this topic for the next few minutes. Let me also tell you a few things about Orfium. Orfium is a relatively new company that in the last 5 years is at the heart of the music industry, powering with innovation and technologies. Orfium has a deep industry expertise and with data research and products solve challenges across industry. We are doing claiming on UGC platforms, empowering major music companies to administer rights and collect royalties from YouTube. Now on to our problem. Genre classification is of course a classification problem. Let's talk about what a classification problem is. In such a problem, we are given a data point and a set of classes, and our aim is to build a classifier. The main functionality of a classifier is to find the one class among that set of classes in which our data point fits best. More specifically, in a genre classification problem, our data point is an audio file, and the set of classes is a list of some music genres. The aim of the classifier is to find the genre of the song. In our case, we have an extra functionality. For example, here we can see that the example audio file goes into the genre classification system and we have a list of the 10 music genres at the output. Each genre is also followed by a score. The score is the actual probability of the audio file to belong to that category. For example, we have a 0% probability for our audio file to belong to the hip-hop genre, whereas we have a 20% probability for our song to belong to the country genre. Someone would wonder why solving this problem would be beneficial. By solving this problem, we can automate a decision usually made by humans and incorporate it into a system that helps humans. This means that we can remove a trivial task and leave time and space to the people to focus on more difficult tasks that can be successfully solved automatically. A great example of this is the role of this system to the claiming team of our company. Let's talk about how this is going to be done. First of all, let me tell you what is the claiming team. The role of claiming team in our company is to find videos that contain music that belongs to Orfium's clients. This service will help them filter the videos they review according to the genre of the music they contain. It has been observed that some genres, such as pop, tend to be more popular, and thus it's more possible for the video containing pop music to be claimed. Another way is to be used as a recommendation system. This system suggests to the claimer similar videos as the ones they have already claimed, according to the music genre again. But how are we going to solve this problem? We are going to follow a data-driven approach based on deep learning methods. First, we want to gather as more data as possible. Then we have to extract useful features from that data. In our case, data are audio files, and the useful features are spectrograms, chromograms, and other transforms. After that, we are going to feed those features in a neural network that learns from the data and is then capable to classify songs that it has never seen before. As this is a research problem, it involves a lot of trial and error experiments and these kind of things to improve the accuracy of the model. In the previous slide, we talked about feature extraction. What is it and why we need it? A song, in its raw form, is a waveform. This waveform shows us how the amplitude is changing over time. However, this representation is not useful enough to be able to distinguish the genre of a song. What we can do is transform the data into a form that includes information about both frequency and time, and end up in a useful representation that can help us actually distinguish the genre of a song. Also, this representation is a 2D array. This means that we can treat it as an image and take advantage of the great progress of deep learning in the field of image classification. Here we can see the approach we followed regarding the model architecture. The architecture we used for our model is usually used for image recognition tasks. And as we can see in this image, the input of the network is an image. Then the image is followed by a few convolutional layers. The role of convolutional layers is to extract useful features from the image. These features are spatial features. In the first layers, more general features are extracted, and as we proceed towards the end of the network, the features become more specific, more task-specific. After the convolutional layers, we have an MLP. The role of the MLP is to combine the features extracted by the convolutional layers to make the final prediction. As we can see here, the final prediction is one of the 10 classes we can see at the top of the network. Here we can see the image that we feed into our model. In our case, the image is a 2D array that represents the energy in different frequency bands over time. Even though this may sound as a complicated term, we can see that it is an image. That's why we can use the network presented in the previous slide, which is a network used for image classification. Now let's talk a bit about the data that we used. For the training and evaluation process, we used one of the most well-known datasets for audio classification, the GTZAN dataset. This dataset is a good reference point as it is often used in research. This means that every time we have a result from our approach, we can compare it to the published results, and then we can tell if it is good enough or if it needs improvement. The GTZAN dataset consists of 1,000 30-second long songs equally distributed in 10 classes. Each class represents one of the 10 most popular music genres. Before we talked about feature extraction, but before actually applying feature extraction to our data, we need to perform some preprocessing on them. The first thing we do is to split the songs into small overlapping clips. In this way, we increase the amount of data available for training, and we can also perform voting among the genres of the clips consisting a song. After that, we split our data into balanced train validation and test splits. Now is the point where we perform the actual feature extraction. We extract various features and we train our model on them. We try different features and perform different trainings to decide which type of feature gives us the best results. Some of the features that we try are the STFT transform, the MEL spectrogram, the MFCC transform, and so on. Here we can see the results of those trainings. We can see that we have two columns of results. The first one is the accuracy we obtained without voting among the clips consisting a song. The next column is the accuracy with voting among the clips of the songs. As we can see, the voting procedure improves the accuracy at an about 10% rate. This means that it's a very useful process that we are going to actually incorporate into our method. After training, apart from observing the accuracy of our models, we also do another type of analysis. We compute the confusion matrix of our models. The confusion matrix is a representation that can tell us which are the classes that our model is better at and which are the ones that our model struggles with. This analysis gave us the idea to combine different classifiers. This method is called CrossClassifier Voting and is used to combine the strength of each model. To do that, we choose models that make complementary mistakes. Here we can see the results of this procedure. In the first two rows, we can see the accuracy obtained by two different models. And in the following rows, we can see the accuracy we obtained by combining those models. As we can see in the last row, we managed to get an accuracy of 93%, whereas the single models had an accuracy of 90% and 84% respectively. The final accuracy, apart from being encouraging because it improved the accuracy we had by the single models, is also very encouraging because the state-of-the-art model in the same dataset has an accuracy of 94%. This means that we are pretty close to that. Here in this diagram, we can see how the training process can be summed up. First, we have our data. From that data, we extract two different types of features. The first one is the STFT transform, and the second one is the MFCCs and deltas transform. These features are fed into an architecture. After the training process, we end up having two different trained models. The first model is trained on the STFT transform, and the second model is trained on the MFCCs and deltas transform. And here in this diagram, we can see the prediction process. We start again with data. In this case, data can be a song. From this song, we extract again two different types of features. First the STFT and then the MFCCs and deltas transform. These features are fed into the model. The STFT features are fed into the model trained on STFT, and the MFCCs and deltas features are fed into the model trained on MFCCs and deltas. Then, the predictions obtained from those models are combined by performing cross-classifier voting, and then we end up with our final prediction. Our final prediction is a genre of the song we had in the input. What can be done next? First of all, we are in the process of deploying the model as a prototyped service, which is the most important step at the moment. After doing that, we can produce a second version of our model. To do that, we should first enrich the dataset with more data so that our model becomes more robust. By doing that and adding more data to the training process, we can also expand the model to be able to classify more genres. Finally, we can adapt the model so that it can find some genres. For example, it can be able to identify the different genres of pop or the different types of rock. That was it. Thank you for your attention. I hope that you find the presentation quite interesting, and I would be happy to answer any of your questions now.
It was a very interesting speech, very well presented. I would say it was very refreshing to see a young data scientist presenting to us. You represent the next generation, I would say, of technologists and data scientists in Greece. So it's great to have you here.
It's great that you're giving me this opportunity as well. So thank you for that.
That's excellent. Very nice. Very nice. Obviously, the first question it pops in my mind and I would like to ask you is if you would advise other young developers who are interested to take the path of data science, what would you advise them? Would you recommend specific platforms to learn, languages? If someone is starting right now, what would you tell them?
Okay, from my experience, which is not very long, I can say that learning Python is very useful. and also practicing with TensorFlow and having an understanding of data. And in this way, like practicing with pandas and this kind of libraries is very helpful. And I think that someone should first learn those things. Yeah, that's it, I think.
Okay, great. Another question that came from the audience, which they found your presentation interesting. I guess I have questions here for you. Has your model been trained only with the publicly available data set, or have you used Orfium's data as well?
Yeah, for now, we have only used public data because, as I said in the presentation, in this way we can actually test if our model is good enough. Because if a model has been trained on a public data set, that means that there are also other models out there. So we can compare the accuracy we achieve. But as a next step, for sure, because working at Orfium, we have more data than those that are publicly available, we have to use this data as well.
Okay. Now, another interesting question here. What type of validation did you use to generate your accuracy scores?
Just the accuracy. I mean, the amount of correctly predicted genres divided by the total amount of songs.
Okay. Okay, is the recognition model available as an API? If not, do you have any such business model in mind?
We are currently working on it. This is the next step after actually designing the model, training it, and evaluating it. We actually trying to deploy it as a service now for our claimers first.
Okay, very good. Another one. May I ask if you also use C++ as the programming language because of the matrices? I guess is the question, because of the matrices that you're using.
No, only Python.
Okay. All right. And we have so many questions here. You become very popular. Well done. Apart from classification, can your model be used for other applications as well? For example,
No,
can it actually create music of a certain kind?
No, it's actually only for classification, but apart from classifying genres, it can be trained for other classification tasks. For example, mood, which is also a quite interesting problem apart from the genres.
Okay. Okay, great. Those were the questions. I think that it pretty much covers the question part. Thank you so much. It was a great presentation. We really enjoyed it, and I hope you had fun as well.
I did. Thank you.
Okay, great. So take care for now. We hope to see you again soon on another event of ours.
Me too.
With another interesting topic.
Me too. Thank you again.